Hello everyone, my name is Mingyu Song. Today I'm going to tell you about a work that I did with Mingbo Cai and Yao Niv on learning multidimensional rules via value-based serial hypothesis testing. Since the beginning of this pandemic, I've developed a new baking hobby, as almost everybody else. This wasn't very easy for me in the beginning, because there seems to be so many dimensions that could be relevant. And even if I follow the exact same recipe, I couldn't get the same result every single time. However, I didn't give up. As I kept trying, after experimenting with different combinations of the conditions, I was finally able to get the hang of it. This brings out my research question. How did this learning happen? How did I actually acquire the rule for baking a great bread? And to put it in a more scientific way, how do humans learn about multidimensional rules with probabilistic reward outcomes? To study this question in the lab, we designed a learning task. The participants were asked to build stimuli like these ones that vary along 3 different dimensions: color, shape, and pattern. On each trial in this task, they would select what features to use for each of the dimensions. They could also decide to not select anything for any of the dimensions. In that case, the computer would just randomly pick one for them. After they are done with their selection, they would see the resulting stimulus and then also the reward outcome. Either they got a point or they didn't. The goal of the participants was to earn as many reward points as possible. And among all the stimuli, some of them are more likely to generate reward than the others. And this is determined by the underlying rule for that particular game. Each game has a different rule, and there are different complexities of rules. Depending on how many dimensions are relevant, there are 1D, 2D, and 3D rules. And within each relevant dimension of a rule, there will be one feature that is more rewarding than the other two, and we call it the target feature. For example, I can create a rule by saying that both color and shape are relevant dimensions. And I will also specify the target features. For example, blue for color and circle for shape. And this will make a 2-dimensional rule. Then the reward probability is determined by how many target features there are in the stimulus. If the stimulus contains all the target features, the reward probability will be 80%. If the stimulus doesn't contain any of the target features, the reward probability will be only 20%. If the stimulus contains a subset of the target features, the reward probability will be somewhere in the middle. So in general, the more target features there are in the stimulus, the higher the reward probability is. In addition to the complexity of the rules, we also manipulated whether this information was given to participants or not. In known games, we would tell the participants how many dimensions were relevant. And in the unknown games, they were not given this information. So this will give us in total six task conditions. We ran this experiment on mTurk and collected data from 27 participants. I'm showing you here the performance learning curve for each of the task conditions. Different columns are different task complexities, from 1-dimensional rules to 3-dimensional rules. The red curves represent the known condition, and the blue curves represent the unknown condition. As we can see here, all the curves go up over the course of a game. This means that people were able to learn to select more target features over time. When the rules were more complex, people's performance were worse, and their learning was also slower. There was also an effect of task information, but it's only in 3D games. People learned better and faster in the known condition than in the unknown condition. Participants' choices were also affected by task condition. Here I'm plotting the number of features selected by the participants on any given trial. Remember I told you before that participants could decide whether or not to select a feature for any of the dimensions. So this number of selected features could range from 0 to 3. As we can see here, in known games, people tended to select more features when they were instructed that the rule was more complex. However, in the unknown condition, there was no difference in the number of features selected across the conditions, and people seem to be acting in an average way. Knowing that the participants were able to learn, naturally the next question is how? Can we characterize people's learning strategy in this task? And the second question is, knowing there's behavioral differences across conditions, can we explain why? To answer these two questions, we developed a few computational models, drawing inspiration from the literature. It has been shown that there are two different learning systems that are often involved in representation learning. One of the systems is value-based. It is incremental learning via trial and error experiences. And the other is rule-based. It explicitly represents rules and evaluates them. In order to evaluate these two learning systems and see which one is used in the current task, we designed two models. For the value-based system, we consider a feature-based reinforcement learning model. It learns feature values for each of the 9 features and combines them when evaluating a stimulus. For the rule-based system, we consider a serial hypothesis testing model. It assumes that participants only test one hypothesis at a time. If the reward outcome they get support this hypothesis, they will stay with it. And if the evidence is against it, they will randomly switch to a different one until they were able to find the correct one in the end. We fitted both models to participants' data and compare how well they predict choice behavior. As a baseline, we also considered the Bayesian observer model. But as we can see here, the Bayesian model actually doesn't predict behavior very well. This is potentially because it requires an extensive amount of computation and memory load, which was probably not very possible for human participants. Compared to the Bayesian model, both the feature RL, the feature reinforcement learning model, and the random switch serial hypothesis testing model fit better to behavior. And more importantly, we also considered a hybrid model that combines both strategies. And this model gave the best fit. This suggests that both learning systems were involved in this task. And knowing that there's evidence for both systems, the next question we wanted to ask is, how are they integrated? And further, how much does each of the systems contribute? We answer this question by comparing the hybrid model to each of the component models. The difference in likelihood will give us the contribution of the other component. Here I'm showing you the results broken down for all 6 game conditions. First, let's look at the known games in the red bars. As the rules become more complex, we can see that the contribution of hypothesis testing decreases, but the contribution of reinforcement learning increases instead. This also, specifically in 1D games, the participants seem to be exclusively using hypothesis testing strategy, while in 3D games, they seem to be mostly rely on reinforcement learning. This result makes sense because, for example, in 1D games, there are fewer possible hypotheses. In fact, there are only 9 of them in total. Even if you were to test them one by one, you'll be able to relatively quickly find the correct one. However, in the 3D condition, there are much more possible rules, and testing them one at a time would be very inefficient in this case. To achieve a good performance in the 3D game, the participants would need to actually learn about all the feature values. Now let's look at the unknown conditions. The pattern is very different here. The contribution of SHT and RL don't actually differ too much across the conditions. And there seems to be a fair amount of both in all the conditions, indicating that people are using a hybrid rule. These results together showed us that when learning about rules, people were able to actually use the information about task complexity and balance between value learning and hypothesis testing in a strategic way. To summarize, we studied rule learning with a probabilistic multidimensional task. And we found that human participants used a hybrid strategy of actively testing hypotheses one at a time and incrementally learning all feature values. Their strategy also depended on the task condition. Specifically, if the information of task complexity was available to them, they were able to actually strike a balance between the two strategies in a smart way. That's it for my presentation. Thank you for your attention and your time. I'm happy to take any questions in the lab chat, and also feel free to email me if you have further questions.